Hi, welcome. So we are continuing our discussion of finding the area between curves, and so I'm going to walk through two examples of finding the area between curves. These are sort of our first examples just to get used to the idea. So in this example, let's find the area between the curves Let's do y equals x squared, and let's do y equals 2x. And to make it easier on us, I'm just going to give us the interval a to b to work with. So let's say on the interval 0 to 2. Okay, so we want to remember in general how this works is we take the integral from a to b of f minus g dx, where f is the function that's above and g is the function that's below. So we're taking that top function minus the bottom function. So in order to apply this concept to our specific example, we're going to need to know a little information about the curves we're looking at. So there's lots of ways we could do this. Really, we could just use a graphing tool to graph them. We are going to see in the second example that we could do this algebraically, so we could figure out which one's above or below just by doing a little bit of math without graphing anything. But I just think we really should graph it, and I'm actually going to graph it by hand because I feel like that's a good skill to have. So I have an axis here, I guess some axes I'm going to put in. Let me make sure I get the right one here. Okay, I've just sized this appropriately ahead of time so that I know I have what I need. And we're going to graph the two curves that we have. So the first one I see is y equals 2x, and I'm going to start with this one just because I can see it's a linear function. So it has a vertical intercept of 0. There's like a plus 0 on the end here. And then it has a slope of 2. So I go up 2 over 1, up 2 over 1, etc. And so from this, I can draw my line through these points, and I'm getting my curve y equals 2x. Okay, now my other curve is y equals x squared. So this is just a parabola with its vertex at 0. If you don't remember this, you can plug in points. So if I plug in 0 for x, I get 0 squared, which is 0 for y. Then I plug in 1 squared, I get 1. 2 squared is going to be 4, and I'll know that -1 is 1 as well. So I have my quadratic here, my parabola. And this is my second curve, which is y equals x squared. Okay, and we are finding the area on this interval, which is the space between them. And so we're looking from 0 to 2, 0 to 2, and we're filling in this area in between the curves. So the way I am going to envision this is with the rectangle method. I kind of like thinking of the rectangles as the height, and it's good practice just to be drawing in your rectangles as you go. If I can make my thing draw rectangles, it's surprising how difficult it is. Okay, there is my rectangle, and so we're going to span these rectangles from the left side, so from the 0 point, obviously with the right height, and then we're going to span them all the way up. So we're filling in that whole space with those rectangles. I'm just going to start this one here. So I can blow up that rectangle, and I'm thinking about adding the width and the height as my area. So my little width is a dx, and my height here, I see that the top function is 2x. And so then I'm subtracting off the bottom function, which is x squared. So my height of each of these rectangles, the top function is 2x, and the bottom function is x squared. So we could write it out even. We could say 2x is above, and x squared is below. And that's specific to the interval we're looking on. So if you look later at different parts in the function, so in the negative x values, we actually have x squared being above and 2x being below. So you kind of just have to know where you're looking and which interval, because it'll change which function's above or below depending on where we are. Okay, so we have everything we need. Remember, we're trying to find the area. We're going to sum up all of these rectangles. So we're starting at 0 and going to 2. I'm using the integral for my sum, and I'm taking the integral of 2x minus x squared dx. Remember, you can always think of this as a height times a width. Okay, but this is our integral, and now we just solve this. So let's go ahead and do that. I think you can probably do it along with me. This one isn't too bad. So we do the integral from 0 to 2 of 2x minus x squared dx. Each of these are just the power rule for integrals. If you wanted, you could split them up. I might do that just to really show it that way. So let's do the integral of 2x, and then we'll subtract off the integral of x squared. Okay. So the antiderivative of 2x is it's 2 times 1/2 x squared. So I've added 1 to the power, so it's 1 plus 1 is 2. And then I'm evaluating that from 0 to 2. Then my second integral, I'm taking the integral of x squared, that's 1/3 x cubed, and I'm evaluating that from 0 to 2 as well. Just a comment too, I stumbled over myself because this is what I was thinking of. The 2 and the 1/2 at this x squared are going to undo each other, so it's actually just x squared. And that makes sense if you think from one to the other. The derivative of x squared is 2x, so that makes sense. Okay, let's evaluate these. So I substitute in 2 for x, and I subtract off 0 for x. And then I minus the second integral evaluated, so I do 2 for x minus 0 for x. So I've just substituted in 2 and 0 where appropriate. And really now, this is just a problem of simplifying and getting fractions together. So the actual hard part, or the new part of integrating, we've already done. We set up our integral. Solving the integral is actually a review. And now we just need to get a solution. So I'm seeing I have 4 here, and then in my second part I have 1/3 times 8, and I'm getting rid of both of those terms with the zeros since the 0 is times itself is 0. And so I have 4 minus 1/3 times 8, which I'm going to write this as 12/3, so 4 is 12/3, and I'm subtracting off 8/3, which is getting me 4/3 as my final answer. So, like I said, this is just some fractions and simplifying things to get the answer we want. But we did it. We got a final solution, and this is the area between those two curves on that interval, 4/3. All right, so that is that first example. We have now found the area between the curves. And for me, I kind of like to write a final statement. So I use this triangle with the dots to represent a therefore, or a conclusion. And I'm going to conclude that the area between the curves is 4/3. That just helps me put the answer in context. Okay, so that is our first example, our first time finding the area between curves. Okay, I'm going to do another example now. So we're going to find another area. This time, let's find the area between let's say we have the curves y equals x cubed, and let's do y equals the square root of x. Okay, so this time I'm not giving us a bounds or an interval, and so we're going to need to find that ourselves. So no bounds given on this one. We're going to need to figure that out. Okay, so if I think about these curves, I'm thinking I sort of know what x cubed looks like, and I sort of know what the square root of x looks like. So if I'm just thinking kind of in my head about what these graphs look like, I can draw x cubed. It looks something like an S-shaped doodad. And then the square root of x starts at x equals 0 and kind of goes off. So this is just my recollection of what these graphs look like. And so I'm thinking here that the x cubed function is the lower function, right? So it's sort of underneath. So I think that the square root of x is above. But just looking at it, I don't know where they intersect. So we're going to need to figure that out so we can get the bounds here to find this area. So the process to do this, you can imagine we can graph this, but we can also do this algebraically, and sometimes that is nice if graphing is going to be hard or you don't have a graphing tool with you. Most of the time we can just graph things using the internet or some other device, but I just like to show you too that we can do this algebraically in case that is interesting or more useful to you. So we can do this graphically or algebraically. Okay, so let's do the geometric way first, just to show you what that looks like, and then I'll show you, we'll kind of confirm our work using the algebraic method. So let's start with geometric. Oh, sorry, I want to say graphical, I think. All right, so let me put in some axes for us and we can graph these things. I got some ready for us ahead of time, so let me put those in. You could use Desmos or a graphing calculator for this if you wanted. So if I'm thinking of the square root of x, first, let's say, I can substitute in values for x to help me make sure I know where this goes. So when I have x is 0, I'm getting 0. When I have x is 1, I'm getting 1. And we could do 2 and more, but we're not going to need to go that far. And maybe you want to do 1/4. So the square root of 1/4 is 1/2. And so that's another point we can put in. And this tells me that the shape of this is something like this. This looks like how I drew it earlier. So this is the square root of x. Okay, now I need to put in x cubed. So my next function is x cubed. We can imagine putting in 0 for x, we get 0. 1 for x, we get 1. And maybe just to get another point, we want to put in a half. So when we do a half cubed, we get 1/8. So that's something down here. And if we do -1/2 cubed, we get -1/8. So I'm going to just put in those points as something for us to have extra. I'm assuming you've probably seen the x cubed graph before, and so this should look like that S shape we were talking about earlier. This is my x cubed. So here I'm seeing that the intersection points are at 0 and 1. So I'm going from 0 to 1. And these are meant to be x values, so my x's start at 0 and they go all the way to 1 on the x. So maybe I'll put this down here just to represent that. Okay, so this is how I sort of know which function's on top and then which one's on the bottom. And we could draw my rectangles again just to get that going, since that might be helpful to us when we do the integral. So if I look at my little rectangle, with the height is going to be the square root of x minus x cubed. So that's the square root of x minus x cubed. And again, my width is a dx. It's a little change in x. Okay, so this is how we would do it graphically. I love graphing things and using that sort of way to look at it. I like seeing the visuals, but sometimes it's just nice to have an algebraic way of doing things. So let me talk through that really quickly. So let's slide this over here. Actually, I can just do it below. So let's go down here and do the algebraic way. So our whole task here is that we're trying to figure out the bounds, and we're also trying to figure out like which function is above and below. So to find the bounds, we're going to set the equations equal. So that's really us finding the intersection points of the two functions. So by setting the equations equal, we're figuring out like which x values they have in common, and that tells us where they intersect. So we're looking at the square root of x equals x cubed, and I'm going to solve for x. So I'm going to square both sides. I'm getting x is equal to x to the 6th. So squaring the square root of x got rid of the square root. And now I just need to solve. So I'll move the x over to the other side, subtracting it. Then I'll factor out an x. So this is x times x to the 5th minus 1. And then I have two things multiplied together equal to 0. So I can split this up into two pieces. I have 0 equals x, and 0 equals x to the 5th minus 1. And now I just have to solve. So remember, we're trying to find the bounds of the integral. We're trying to find where these two equations, these two curves intersect. So I have 0 as one of my points, and then I just need to move the 1 over and take the 5th root, but x to the 5th equals 1. The solution to that is just 1, like 1 to the 5th power is 1. So I'm getting my two values that look like what we got with the graphs. So I'm getting x is 0 and x is 1. These are the bounds of my integral. Here. Okay, so really this method works like you can use this to find the bounds anytime you have any functions. So sometimes like they might be hard to graph, or like maybe you don't want to graph them and you just need to find the intersection points quick. You can just set them equal to each other and solve that way. So this got us the bounds, but now we need to know which function is on top and which function is on bottom, or which function is above and which function is below. So I'll set that over here. So in order to see which function is above, basically what we want to know is on that interval from 0 to 1, those are our bounds, which function has a higher output? So like which one would be above, like have a greater output? So to do this, we're going to choose a test point. In the interval 0 to 1, and we're going to plug it in to both of the functions. So let's choose x equals 1/4. This one just kind of happens to work well, so I'm choosing it. And remember, we're going to put it into x and x cubed to see which function is above or below. So when I put 1/4 into the square root, I'm getting 1/2. And when I put 1/4 into x cubed, I'm getting 1 over 64. So 1/2 is bigger than 1/64th, and this tells me that the square root of x is above, because 1/2 would be above 1 over 64. And so just by doing this, I can see that the square root of x is above, and then I would subtract off the x cubed to get the below function. So really, this algebraic way kind of takes some work and takes some like fluency with doing the algebra stuff. So personally, I kind of prefer to graph it, especially since we usually have those tools at our disposal. But this is just nice to have the other method, like I've said. Okay, so we have our algebraic method. We found that it was from 0 to 1, and it was square root of x minus x cubed. And we found the same thing with the graph. So we feel really good about that, hopefully. And now we're going to set up our integral. So I'm looking at the integral from 0 to 1 of square root of x minus x cubed dx. So I'm looking at the area under the curve, or sorry, between the two curves from 0 to 1. And now we just need to solve this. So this is now just an integral problem, something you've been practicing to do, and it takes a little while after this point. We have to do a lot of manipulation with some fractions and stuff. So if that is not super interesting to you, you could maybe like pause and try to do it on your own and then just like check the final answer. So that's one option, or you can follow along with me. I'm gonna do it. I just want to give you a heads up that it's going to take us a few minutes to finish this problem, just because it kind of happens to involve lots of fractions. So the important thing we just learned is how to find this integral. How to set up this integral to find the area that we were looking for as asked in the problem. So this part is now just sort of review, but let's do it. It's good practice. Okay, so in order to integrate this, I'm going to rewrite that square root of x as x to the 1/2. That just allows me to view it as a power function. And so when I do this, I just add 1 to both of these exponents and divide by the new exponent. So I'm going to add 1 to 1/2. I'll write it all out. I thought maybe I wasn't going to, but let's do it. So I added 1 to that exponent, and now I'm going to add 1 to the exponent of 3 and divide by that. So I'm just following the power rule here, or sorry, I guess the power rule for integrals. And then I'm evaluating from 0 to 1. So I'm getting 1 over 3/2 x to the 3/2 minus 1 over 4 x cubed to the 4th, And this is all evaluated from 0 to 1. So if you wanted to be like really formal, you could probably put parentheses around this. Ooh. Sometimes I just don't do that. I get kind of lazy. But it's not really good to be lazy. You probably want the parentheses there. Okay, so now we just need to simplify and solve. I'm going to do a little more manipulating here before I evaluate. So 1 over 3/2 is 2/3. And then I'm going to rewrite x to the 3/2 as the square root of x cubed. That just helps me like have it written a little better. And then I still have that 1/4 x to the 4th. And I'm evaluating from 0 to 1. So let's evaluate. First I plug in 1 into my equation. Then I take that result and I subtract off what I get when I plug in 0. Which we can see that 0 is just going to go away, so that's pretty nice for us, but I'm going to write it out. So on this first portion, I have 1 cubed, that's just 1. Square root of 1 is 1, and that whole thing goes to 1, so I have 2/3 times 1. And then I'll have 1/4 times 1 as well. Okay, and then my second part, as I mentioned, square root of 0 is 0. 0 to any power 0, so this is just 0 minus 0. And it's all 0. Okay, now we just have to wrap up. So I have 2/3 minus 1/4, and then 0 left. And so I'm going to get a common denominator here. I see that it is 12. So I'm going to have 8/12 is 2/3, and 1/4 is 3/12. So combining those, I get 5/12, and this represents my area between the curves. Oof, okay. So we could conclude the area between the curves is 5 over 12. And there we go. That's our second example. So this time we were given just the two formulas, the two curves that we wanted, and we needed to do some extra work to find the bounds and then set up the integral and solve. That's it for this video. I'm going to do more examples of finding the area between curves, some other things that can come up in the next one. Thanks so much for watching, and I will talk to you soon.